A spider web looks almost weightless. A few nearly invisible threads stretch between branches, moving with the wind, yet somehow capable of stopping an insect flying into them at speed. And that creates a strange engineering question: how can a material produced inside the body of a spider possess a combination of properties that engineers still struggle to reproduce? The answer isn't simply that spider silk is stronger. Steel is extremely strong and stiff, while spider silk behaves very differently. It can stretch significantly, absorb energy, and still resist breaking. That combination is what makes the material so unusual. Imagine an insect crashing into a web. If the web stopped the insect instantly, the impact would concentrate enormous force at one point. Instead, the silk stretches, the surrounding strands move, and the energy is distributed through the network. The web doesn't need to stop the insect instantly. It needs to survive the impact. That ability to absorb energy before breaking is called toughness, and it is one of the most important reasons spider silk has attracted the attention of materials scientists. But toughness isn't the only reason. Spider silk is also incredibly light compared with steel. So engineers don't only ask how much force a material can withstand. They ask how much performance they can get from every gram of it. And this is where spider silk becomes truly remarkable. It combines high tensile strength, elasticity, toughness, and very low density in a single fiber. But none of that happens by accident. The secret is hidden inside the silk at a scale far smaller than the thread itself. Spider silk is made from proteins arranged in a highly organized structure. Some regions are more flexible, allowing molecular chains to move and stretch, while other regions form tightly organized crystalline structures that help reinforce the fiber. One part gives the material room to deform, while another helps it resist failure. Together, they allow the silk to absorb large amounts of energy without simply tearing apart. And now the real mystery begins. A spider isn't running a factory. It doesn't need a furnace, an industrial press, or a massive production line. It starts with something that looks completely different from the finished material, a concentrated liquid containing silk proteins. Somehow, that liquid becomes a solid fiber with remarkable mechanical properties. So the real question isn't only, why is spider silk so strong? It's this: how does a spider turn a liquid protein solution into a high-performance fiber? To answer that, we have to go inside the spider. Inside the spider's silk gland, there is no finished thread. There is a concentrated protein solution, and the spider has to transform it into a solid fiber at precisely the right moment. As the silk moves toward the spinneret, the environment around those proteins gradually changes. Water is removed, the chemical conditions shift, and mechanical forces begin guiding the molecules into a more organized structure. The spider isn't simply producing a substance. It's controlling a manufacturing process. And this distinction matters, because the final properties of spider silk depend not only on the proteins themselves, but on how those proteins are assembled into the finished fiber. As the fiber is pulled, the flexible regions of its molecular structure can deform and stretch. As the force increases, the more organized crystalline regions help carry the load and resist failure. That's why the silk doesn't have to choose between strength and flexibility. It can combine both. And this becomes especially important when the silk is part of a web. Wind moves the structure. Branches shift. Insects collide with it. The forces are constantly changing. Instead of behaving like a rigid cable that tries to resist every movement, the silk can stretch and absorb some of the energy, while the network distributes the remaining force across multiple strands. The material and the architecture work together. That's a powerful engineering idea, because the strongest material isn't always the one that simply resists deformation. Sometimes the better material is the one that controls how energy moves through the structure. But the spider has another advantage that is even more difficult for humans to reproduce. It doesn't need to manually position every protein molecule. It creates the right chemical and mechanical conditions, allowing the molecules to organize themselves as the fiber forms. In other words, the spider isn't assembling the material piece by piece. It's controlling the conditions that allow the material to assemble itself. And that changes the entire engineering problem. Scientists can study the proteins. They can analyze their molecular structure. They can even use engineered biological systems to produce spider silk proteins. But producing the proteins is only part of the challenge. The difficult part is turning them into a fiber with the same combination of strength, elasticity, toughness, and low weight found in natural silk. Because knowing what a material is made of isn't the same as knowing how to make it work. And that's exactly why spider silk remains so difficult to reproduce. So why not simply collect the real thing directly from spiders? At first, the solution seems obvious. Raise millions of spiders and collect their silk. But spiders are not ideal industrial livestock. Many species are territorial and don't tolerate dense populations, while their silk production is far too limited for conventional large-scale farming. So scientists had to change the question. Instead of farming the spider, what if another organism could produce the silk proteins? Researchers have explored microorganisms, genetically modified organisms, plants, animals, and even silkworms. These systems can produce spider silk-related proteins, but the hardest part remains the same, turning those proteins into a fiber that reproduces the properties of natural spider silk. Because spider silk isn't defined only by what it's made of. It's defined by how it's made. The spider controls concentration, chemical conditions, water removal, molecular organization, and the mechanical forces involved in spinning. Change that process, and you can change the final material. That's why copying the spider's genetic instructions isn't enough. We're not simply trying to reproduce one protein. We're trying to reproduce an entire manufacturing system refined through evolution. And this brings us back to steel. Spider silk isn't a universal replacement for steel. Steel is stiff, predictable, durable, and can be produced on an enormous industrial scale. Spider silk solves a different engineering problem. Its real advantage is the unusual combination of high tensile performance, toughness, elasticity, and extremely low weight. That combination makes it interesting for applications where every gram matters, including advanced composites, specialized fibers, protective materials, and some medical technologies. But perhaps the most fascinating part of spider silk isn't what engineers might eventually build with it. It's what the material teaches us about engineering itself. The spider wasn't trying to create something better than steel. It wasn't designing a bridge or building an aircraft. It simply needed a fiber capable of surviving the forces of its environment. And evolution refined that solution until a tiny animal could manufacture a material with an extraordinary combination of properties. Now humans are trying to reverse engineer it. Not because spider silk can replace everything steel does, but because it demonstrates something we still struggle to achieve: strength, toughness, flexibility, and low weight working together in one material. So the next time you see a spider web stretched between two branches, don't just see something fragile. Look closer. Inside that nearly invisible thread is a molecular architecture and a manufacturing process that engineers still haven't fully mastered. A spider turns liquid protein into a high-performance fiber. Humans built enormous factories to make steel. And yet, when it comes to creating a lightweight material that can be strong, flexible, and remarkably tough at the same time, we're still studying the spider. Because sometimes nature doesn't give engineers a finished invention. It gives them a problem worth decades of trying to solve.